Hello everyone, Mr. Minnick is my name, math is my game, and I'm joined today by a super excited group of fine young ladies and men who are excited about learning Chapter 8, Section 3, Graphing General Rational Functions. So, last week we graphed simple, LOL, rational functions. Those were hyperbolas. This week the things that we're going to graph look like they belong in health class. Or biology, maybe. So anyway, Chapter 8, Section 3, Graph General Rational Functions. If I'm taking notes, I'd write down the title. Key vocabulary, we've discussed end behavior in Chapter 5. I wouldn't worry about that. Asymptotes, we've mentioned that. You know that it's a line the graph approaches. Rational functions, that's what we've been talking about all chapter long. So I think we should just get right to it. How's that sound? Like a winner? Here we go. There's so much information on this first page. I'm going to leave it up here a few minutes. There is 3 different things going on in this table. So rather than writing all this stuff that they have here, let me just kind of summarize that, because that's pretty intimidating to look at. They're just saying, let P of X and Q of X be polynomials. Okay. Well, I guess that all is important. I guess I'm going to leave that up there. I'll let you write that down. Summarize it however you would, but all that stuff's important. The numerator is some kind of polynomial. The denominator is some kind of polynomial. Now, this definition of a polynomial, all this mess, maybe you don't need to write all that down, because that was in Chapter 5. That's kind of scary. They're just saying we got a polynomial over a polynomial, and there's no common factors. There's no common factors. And then they're going to talk about the characteristics. Kind of interesting, that first point they make about the x-intercepts being the numerator's solution. If you set the numerator equal to 0 and solve, you'll get the x-intercepts. Number 2 is saying that if you take the denominator, set it equal to 0, that's how you're going to find your vertical asymptotes. Then they're talking about horizontal asymptotes too, and that's determined by the powers, by the degrees, by how the numerator compares to the denominator. So I do apologize for there being vast quantities of information, but this kind of sets the stage for all the examples we're going to look at. So if you need a few minutes, I'll certainly afford you that time. Speaking of time, you all heard about fruit flies, right? Time flies like an arrow. Fruit flies like a banana. Took me a while to get that one. I never quite got that one. There's going to be a question on your test about the tractor joke too. So, yeah, the magical tractor turns into a field. And on the Kahoot, in a couple days' time, there's going to be a question about my birthday, which is October 5th. And then also about my car's transmission. It's a 6-speed manual. My birthday's October 5th. I love the fall. Great time of year. 18 something, yeah. So again, number 1's kind of saying if you need to find the x-intercepts, you set the numerator equal to 0 and solve. Number 2 says if you need to find the vertical asymptotes, you set the denominator equal to 0 and solve. Number 3 says there's going to be at most one horizontal asymptote. Sometimes there isn't one. And if you wrote down the table before, the table below says if the numerator is like a linear and the denominator is a quadratic, something like that. Or maybe the numerator is just a number and the denominator is some kind of linear expression. Then the line y equals 0 is going to be a horizontal asymptote. If the numerator and denominator both are of the same degree, in other words, you have like a quadratic over a quadratic, then you look at the leading coefficients and that's going to determine where your horizontal asymptote is. And then the last part says if the numerator is a bigger polynomial of higher degree than the denominator, then there's not going to be a horizontal asymptote. So sometimes there are no horizontal asymptotes. And then it goes on to say that the end behavior of that graph, if you were just to divide the first two terms, the end behavior is going to be kind of like that. Those of you who are going to take college algebra next year, they talk about slant asymptotes. Those are kind of cool. We might encounter one of those on today. So I'm going to put in a specific instance in that bottom part of the table. You know, something like if we had 1 over x, y equals 1 over x. If you recall, that had a horizontal asymptote when y equals 0. For the part where m and n are equal, you know, if we had something like y equals 7x squared plus 5 divided by something like x squared plus 1, what they're telling us there is that the line y equals a over b, or 7 divided by 1, or y equals 7 would be where the horizontal asymptote would be. And then in that last condition, we might have something like y equals x plus 1 over x squared plus 5x plus 3, something like that. If we have something like that going on, actually no, I take that back, that's wrong. I just messed that up. Let's try that the other way around. X squared plus 5x plus 3 over x plus 1. If we had something like that, the end behavior of that one, if we just look at these first two terms, it would kind of be like y equals x, which is kind of like a line. So what we're saying is the end behavior of that graph, whatever that graph happens to look like, the end behavior of that graph is going to do something like that. I guess it couldn't do that. And we might get some slant asymptote type situations. We're going to get some really weird looking graphs here. There is good news. You know what the good news is? On the test, you're going to be allowed to use the calculator. Not your notes, but the calculator. Okay. Is there going to be an essay question about those? Well, the test is 50 Scantron questions. So no. Probably in tonight's homework there's going to be an essay question about it. I would think. Ready to see an example? Or do we need a few more minutes? One more minute. You guys know who René Descartes was, right? French person, gave us the Cartesian plane, otherwise known as our XY axis coordinate system. You guys know what he said. That's a famous quotation, don't you? I think, therefore I am. That's Descartes, in case you ever need to know. There's a funny joke. It says, I think not, and then the person saying it disappears. Maybe it's not funny. Okay, example number 1. Graph y equals 6 over x squared plus 1. Kind of unusual. They say take the numerator and set the numerator equal to 0 to see where the x-intercepts are. Well, if we set 6 equal to 0, that doesn't even make any sense. Do you think this graph has any x-intercepts? Well, we set the numerator equal to 0. There's not even an x in there, right? So there's not going to be any equation to solve. So the point is this graph is probably going to have no x-intercepts. Okay? So that's kind of what this number 1 tells us. So there's really not going to be any x-intercepts. The next thing says, okay, now we need to take the denominator. Let's take the denominator, in this case x squared plus 1. Let's set that equal to 0 and let's solve. So we're going to get x squared equals negative 1. So we'll get x equals plus or minus the square root of negative 1. Is that real? No. That's not real. Well, that tells us where the graph's vertical asymptotes are. Well, there aren't any things. So what this means is the graph's not going to have no vertical asymptotes. So what's going on here? There's no vertical asymptotes. There's no x-intercepts. Let's take a look at the third bullet point. If there is a horizontal asymptote, it's going to be determined by the degrees. In this case, we're looking at that first situation, and we should have some kind of horizontal asymptote because this is 6x to the 0. This should have a horizontal asymptote. Should have a horizontal asymptote when y equals 0. So that's the only thing we know about the graph before we graph it. Kind of weird. So let me sketch in my horizontal asymptote. Here it is. Y equals 0. There's my horizontal asymptote. I don't expect you to be able to graph one of these without a calculator. Can you? Some of them, yeah. This one, you're going to have to plug in a table of values. You could probably get a quick sketch without a calculator. Let's see what happens if we just pick 1. If we pick an x value of 1, we're going to have 6 divided by 1 plus 1, 6 divided by 2, or 3. Everybody see that? This graph's going to go through the point 1, 3. If we plug in a negative 1, we'll get the same thing, because negative 1 squared is 1. That'd be 6 divided by 2. That's also 3. If we plugged in something like a half squared, isn't a half squared a fourth? And a fourth plus 1 would be 1 and a fourth. What happens if we have 6 plus 1 and a fourth? Or I'm sorry, 6 divided by 1 and a fourth. 6 divided by 1 and a fourth. That's going to be smaller than 6, right? Okay, so something smaller than 6. Something smaller than, let's see, 1, 2, 3, 4, 5, 6. Something smaller than 6. We don't know how far up. But what's going to happen is this is going to do something like this. Something like this. And somebody said plug in a 2. Let's see what happens. 2 squared's 4. 4 plus 1's 5. 6 fifths is 1.2, right? So if we plug in a 2, we're going to get something like 1.2. If we plugged in a 3, we'd have 9 plus 1, 10. 6 tenths is 0.6. A little bit more than a half. So do you kind of get an idea what this graph looks like? What's going to happen whenever x equals 0? Hold on. When x equals 0, we'll have 0 plus 1 or 1 in the denominator, and 6 divided by 1 is 6. 1, 2, 3, 4, 5, 6. Okay. So x-intercepts are where the graph crosses the x-axis. Well, the graph doesn't cross the x-axis. There's no x-intercepts. Horizontal asymptote when y equals 0. That's it. That's the graph. Let's see how we did. Let's look on a TI Inspire. See if we got it. We didn't use a calculator. Maybe we could have. 6 divided by x squared plus 1. Oh, hold on a minute though. I think I punched something in wrong, didn't I? Yeah, I didn't put the parentheses. So that x squared, that plus 1's got to go in the denominator down here, right? That's what we had. There it is. Got him? Question? Comment? Concern? Short debate? Long debate? Okay. Well, I'm going to interject an example in here right about now. Kind of a neat one. It's not in the book. Example 1.1. Y equals x plus 3 divided by x squared minus 9. So if we were to look at this, And you know what they say, sometimes you just got to look at it. If we were to look at this, when we set the numerator, this is going to number 1, if we set the numerator equal to 0 and solve, that tells us where our x-intercept is, right? That's our x-intercept. So this graph should have an x-intercept when x equals -3. Point number 2 says if you take the denominator and set it equal to 0, if you take the denominator and set it equal to 0 and solve, that's going to tell you what? Yeah, plus or minus 3, that's going to tell us what, though? When we set the denominator equal to 0. Not the y-intercept, the Virginias. The vertical asymptotes. Vertical asymptote. I'm going to put an asterisk by this one because there's a problem that we'll hopefully see in a little bit. Point number 3 said because the numerator's power is smaller than the denominator's power, this is going to have a horizontal asymptote when y equals 0. Okay, so let's see if we can't. Because the numerator has a smaller degree than the denominator. Anytime that's the case, that's always going to happen that way. And that was point 3 of those 3 points on that one page of notes. So what we know about this graph then is that this graph is going to have a horizontal asymptote when y equals 0. It's not very funny, but we write ha. It's going to have an x-intercept when x equals -3. So the graph's going to go through that point. And that's all we know about it. Oh, wait a minute. Vertical asymptotes, we said, when x is 3 or -3. Wait a minute. When x is 3 or -3? Huh? 2 vertical asymptotes? Wait, there's got to be something going on here. When x is 3 and when x is -3, how can that happen? Yeah, there can't be. Well, if the thing is supposed to have an x-intercept when x is 0. Or when x is -3, I mean. When x is -3, it's supposed to have an x-intercept. I'm scratching my head here. Stand by. So, did anybody notice yet what the deal is with this one? Let's see who took really good notes and who was paying attention. Let's go back to the page 1 of the notes. Remember I started to say you don't need to write all this down, and then I stopped myself and I said you do, because that's all good information. No common factors. Oh man. There's this part about no common factors. All these rules are true if there's no common factors in the numerator and the denominator. So let's take a look at this example that I put in here. This example that I made up. If we were to have factored this, this is x plus 3 divided by x plus 3 and x minus 3. So what happens with the x plus 3's? They cancel. This cancels this, and we're left with 1 divided by x minus 3, which we just graphed last week, didn't we? Isn't that just a hyperbola translated 3 units to the right? Okay, so the graph of that should look something like meow, and something like meow. The graph should look like that, shouldn't it? And it does. But the calculator is going to lie to us. The calculator is going to lie to us. So this vertical asymptote thing, that we can't say anything about vertical asymptotes if there's common factors top and bottom. Oh man. And there's one thing even the best of calculators is going to lie to you about. Even the best of calculators is going to lie to you about. We took the denominator and set the denominator equal to 0 and we solved, right? What happens when the denominator equals 0? When you divide something by 0? It's undefined. So there's going to be something occurring at the graph right in here. At this point right here, when x equals -3, there's a giant question mark. What's going to happen there? You know? Inspire's going to lie to you. You're right. There's a disk something. Yeah, there's a disk something. So let's see what the calculator says. The calculator says, okay, if we graph x plus 3 divided by x squared minus 9, it looks like we're copacetic there, doesn't it? It looks like we're fine. Copacetic is it appears fine, but it isn't. Well, maybe that's the right word. It is copacetic, but it's not. So let's try to zoom in. All I want to do is zoom in right here. And maybe I should trace the graph. When x is negative 3.5, everything's okay. Oh. There's a hole in the graph. It doesn't show up, but there is a hole there. What do you think? Whatever trace is. Well, did we go over this? I mentioned it a long time ago. Yeah, so a hole in the graph, a hole in the graph occurs at the point where there is a common factor in the numerator and denominator. I would love to hear Arnold Schwarzenegger say both of those words in the same sentence. So a hole in the graph occurs at the point where there is a common factor in the numerator and the denominator. If that's not a long enough sentence, I'll extend it. And is called, so in math, whenever there's a hole in the graph of a function, there's a special name for it, 2 words. Well, it is a hole, but what we did, if we look for a second, when we canceled those x plus 3s and x plus 3s, what did we do with them when we canceled them? We got them out of the equation, right? It's an omission. We took them out of the equation. What happens if I were to take a desk and take it out of this room? What's a word that we could say what I did to that desk in the room? I did what? I removed it. And these are called removable. Yeah, it's a removable discontinuity is the word we're looking for. It's a removable discontinuity. A removable discontinuity. I'm going to go golfing. I hope I get a removable discontinuity in 1. That's a really far stretch. Woo! Any questions so far? Okay. Well, let's look at the next example then. Example 2, now we've got that second condition met in that table below. Notice we've got the same power going on in the numerator and the denominator. So the first thing that we should notice is we set the numerator equal to 0, so 2x squared equals 0. X squared is 0 over 2, x squared is 0, square root. When x equals 0, this graph should have an x-intercept there. This graph should have an x-intercept when x equals 0. So the graph's probably going to go through the origin. If we were to factor this, this is like 2x squared over x plus 3 and x minus 3. So when we set the denominator equal to 0, x squared minus 9 equals 0, we get x is 3, x is negative 3. What's that tell us about the graph? That's where there are not removable discontinuities. The removable discontinuities only happen when there's common factors. And we don't have common factors top and bottom. There's 2 vertical asymptotes. Yeah, good. So this graph is going to have 2 vertical asymptotes. One when x is 3, and one when x is negative 3. And this might be one of those graphs that looks like health class. Might. I don't know. So the last thing we need to do then is to consider, well, because of the way the powers are, the horizontal asymptote The horizontal asymptote is going to be when y equals 2 divided by 1, which is just 2. So there's going to be a horizontal asymptote when y equals 2 for this particular graph. There's going to be a horizontal asymptote. It's not very funny, but we write when y equals 2. And then we've got this vertical asymptote when x is negative 3, and when x is positive 3. We got another vertical asymptote. Wow. Wild and crazy looking graph. It is. And we haven't even graphed the thing yet. So maybe we should plug in, well, if we plug in 0, I guess we'll get a 0 in the numerator, and 0 minus 9, which is minus 9. 0 divided by minus 9 is 0. So we're okay with plotting this point. Maybe we should pick 1. Let's see what happens when we pick 1. When we pick 1, we're going to have 2 times 1 squared, which is 2, times 1, or 2, over 1 squared, which is 1 minus 9. 1 minus 9 is negative 8. So we'd have 2 over negative 8. 2 over negative 8 is negative a fourth, right? So when x is 1, y is negative a fourth. And by symmetry, we would get this point over here. Let's pick 2. When x is 2, we'd have 2 times 2 squared. So 2 times 2 squared. 2 squared is 4. 2 times 2 is 8. And then in the denominator, we're going to have 2 squared, or 4 minus 9. So that's going to be what? 8 divided by negative 5. 8 divided by negative 5, so that's negative 8 divided by negative 5. That's negative 1 and 3/5. So that's negative 1 and 3/5. So you kind of get an idea what's going on there. The graph is going to kind of look like this here. Oh man. And then on the other sides, well, we're going to have to pick some other points, like 4, 5, 6, 7. Let's pick 4. Let's see what happens when we go with 4. When we go with 4, we're going to have, is it 32 over something? Yeah, because 4, yeah, so 32 over 4 squared, 16 minus 9, 32 over 7. And that's almost 5. That's like 4 and change. That's 4. That's 4 and what? Is that 4 and 4/7? 4 and 4/7. So at 4, we're going to have 1, 2, 3, 4 and 4/7. So something like that and something like that. If we picked 5, we would have 50. 50 over 16, which is a little bit bigger than 3. So that's getting a little bit smaller now, isn't it? Do you think you have an idea what's going on here? The graph's going to end up kind of going like this, and like this, like that. And what did I tell you? Duck, insert, graphs. What was in our numerator? 2x squared. And then I typed the 2. It didn't like my 2. My computer's overheating. So x squared minus 9 in the bottom. Thank you. So here we go. How'd we do? We didn't do so bad, huh? I'm not going to comment on the shape of the graph, I don't think. Zoom out, menu, zoom out from right about here. Okay. So let's go to the next one. Finally, we've got one where the numerator is larger than the denominator. So what did we say? We said we got to take the numerator, x squared plus 3x minus 4, set that equal to 0. That's going to be x plus 4x minus 1 equals 0. x is -4, x is 1. That's where our x-intercepts are. That's where our x-intercepts are. When x equals -4 and when x equals 1, that's the x-intercepts. So that's our x-intercepts. When you take the denominator, we set the denominator equal to 0. And that tells us where the state of Virginia is. Where our vertical asymptote is, I should say. We're going to have a vertical asymptote when x equals 2. And then what? Because of the nature of this, it's not funny at all. Because of the nature of the powers, there's no horizontal asymptote. But we do know that the end behavior of the graph is going to behave like if we just looked at the first two terms. What's x squared over x look like? Isn't that just a line like that? So think about what that line looks like. That line's going to go like this, and that line's going to go like this, and that's what the end behavior of this graph's going to do. This is a really unusual graph. I'm not even going to say it has what's called a slanted asymptote. There are special names for slanted asymptotes. If somebody looks it up, I might throw them a bone if somebody can tell me what a slant asymptote's actually called. There's a special name for it. So this function was a fraction. There's another name other than slanted asymptote. Somebody in my one class, I think somebody in one of my other classes looked it up. Not diagonal. I'll know it when I hear it. So that's what that end of it looks like. Now, we can kind of see on the left edge that it looks like y equals x, right? But we need to see the other side of it, so I better zoom out. I better zoom out a little bit. Oblique, that's it. Nice, thank you. Good looking out. Shout out to Traves. So what do you think about that one? Do all these rules make sense? Let's look at another one kind of like this. Example 3.1. Y equals x squared minus 10x plus 25 divided by x plus 5. Hey, shouldn't that factor easily? On the chapter test, there's a question, true or false, a perfect square trinomial factors easily. That's true, right? So if we were to factor this is x, yeah, I meant to make the denominator x minus 5, I'm sorry. Hopefully that doesn't mess you up. Do you mind if I make the denominator x minus 5? You still love me? Well, you might not love me in the first place, but anyway. Hey, what's this graph going to have in it because we can remove a pair of factors? A removable discontinuity. But what's this graph going to look like? This graph is going to, well, the asymptote, all those rules kind of don't work so well whenever the numerator and denominator have common factors. If we were to graph this thing, if we were to graph this thing on a calculator, it's going to be undiscernible from that, unless we understand some algebra. You guys know how to graph that, don't you? Remember in Algebra 1? Isn't it just going to look like that? With one exception. A removable discontinuity where? When x equals what? When x equals 5. Well, that's going to be actually right there, isn't it? Yeah, so there's going to be a hole there. And the bad thing is the calculator won't show it to you. Doc, insert. Graphs. So we got a fraction. It was x to the squared minus, bless you, 10x plus 25 divided by x minus 5. Graph it, and it looks just like a line. And it looks like the graph goes through the point when x equals 5. But if we trace the graph, Let's see what happens. Oh. Oh, man. That calculator is wrong, I think. Or maybe it's right. Wouldn't the graph be undefined there? Didn't the Inspire just lie to us? What about the TI-83? What do you think it's going to say? Y equals the quantity x to the squared minus 10x. I said 10x plus 25 divided by x minus 5. Close it, graph it. Value when x is 5. That one says undefined. The Inspire says it exists. Dude, do you mean the 83 is better than the Inspire sometimes? Yes, that's what I mean. I mean, you need to know algebra because at some point technology is going to fail you. At some point technology will be unable to help you. And you need to know. Technology helped us but failed us later. But it did fail us at one point. So let's see if there's anything else we need to look at before we wrap this up. This is math class. We don't read in math class, so we're not going to do that problem, right? So that's it. It's been real. It's been fun. I'd like to take this opportunity to give a shout out to Miss Guy. I'd like to give a shout out to the future Mr. Minnick. He's probably in the back of the room taking notes, even though somebody else thinks he's grading papers or working on something else. He's back there taking copious notes. Good job, Mr. Minnick. Keep up the good work. Any other shout outs? A shout out to Zach Gorby. Right on. A shout out to Katie Sinisvet. A shout out to who? Josh Forsyth. Right on. Any other shout outs? John Laurenchak. Mr. Walker gets a shout out. 5 seconds. 4. Mr. Dobrin gets a shout out. You know, I love when Mr. Dobrin comes on the announcements and says, "May I have your attention, please? May I have your attention, please?" He's got to say it twice. So shout out to Mr. Dobrin, and a shout out to my 6th period class for doing a good job with this, and a shout out to my 1st and 2nd period classes. See you.
Good.